Hey folks, I've got a couple examples, or again, one example of motion of charges in an electric field. And if you can do this one, then any other one I might give you is going to be easier or the same level at most. So you might take a minute to pause the video and copy down the diagram and the list of givens there and the things to determine there. So if you need to, I would do that now. Alrighty. So let me explain what you're looking at and what you just drew. So we have a sheet of charge, a plane of charge. And we're going to assume, it's not drawn to scale, but we're going to assume that this plane of charge, or these two planes of charges, are large compared to how far apart they are. Okay. So again, I can't draw it to scale, obviously, but imagine that these are both large planes of charge. Okay. And the top one has a charge density, surface charge density of negative 100 picocoulombs per meter squared. And the bottom one has an identical positive charge per meter squared of 100 picocoulombs. And the things you're given is you're given those charge densities. You're going to have an electron, of which I'm going to know the mass. You can look that up, and I'll write it down for you in a little bit here. We also know the charge of one electron is 1.6 times 10 to the negative 19th coulombs. I'm giving you the V naught of the electron, which is 4 times 10 to the 5th meters per second, and delta x, the length of the plane, which is 10 centimeters. And so here are the things that we're going to figure out. What is the electric field strength and direction between the plates, where the electron will be traveling? For how much time is the electron between the plates? That's the easy one, by the way. When the electron leaves the plates, so when he's over here somewhere, what's his vertical velocity? And then at what angle does he leave the plates? Okay. So now there's going to be numbers for all these, but we're going to start by answering all four of these questions in terms of the givens and fundamental constants. Okay, and then we'll plug numbers in a little bit. But what's more important is do I know like what to do here? Getting the calculator out is the last thing you need to worry about. All right, so what's going to happen here is these two plates are going to make an electric field. And in a previous video, we talked about that field. For a plane of charge, the field is constant. For a positive charge, the field points away from the plane. And up here, for this negative charge, the field points toward the plane. So in between the plates, you're going to have a field that points upward like so. And I'll draw some representative lines of that. Okay, so there you go. And it looks like that. And I think it's important to draw this out just to have a flavor for if you could see the electric field, what would it look like? Okay, so there is the electric field direction between the plates. It's going to point up from the bottom plate to the top plate. How strong is that? Well, you hopefully would recall, and this is one that I would memorize, for a single plane of charge, so a single one, E for a plane is sigma over 2 epsilon naught. Okay, and epsilon naught's a constant, which we'll write down in a little bit here when we do our numbers. Now, that is the electric field of one plane. Well, that's like, if I just had the bottom plane, that would make a field up of that strength. But I also have the top plane making an additional equal field up. So the total field between these two plates is going to be double this. So the net electric field between the two plates will simply be sigma over 1 epsilon naught. And I'll go ahead and plug numbers in. Sigma is 100 picocoulombs, so that's 100. Now pico is, see, it's milli, micro, nano, pico. -3, -6, -9, -12. So this is 100 times 10 to the -12 divided by epsilon naught, which is a constant, which is 8.85 times 10 to the -12. Now, by the way, at some point, I would suggest you're going to memorize epsilon naught because you're going to use it a lot. Okay. Now, in this example, the -12s cross off. Hey, goodness, that's great. And I end up with, you're just dividing 100 by 8.85, and I get 11.3 newtons per coulomb. Okay, so that's the strength of the electric field between the plates, and it points up. Now, so that's the first thing. That's the electric field. The time. Okay, well, when this electron is in between these plates, okay, if he were a positive charge, he would feel a force upward because positive charges experience a force that's in the same direction as the electric field. Okay, but alas, he is a negative charge. So he is going to feel a downward force, an electric force downward. Okay, now here's the good news. That downward force does not affect his horizontal motion in the least. This is very much like projectile motion. Okay, so by the way, his path will be parabolic as he goes between those plates. Now, so as far as finding the time between the plates, well, I'm just going to use delta x equals Vx times t, or t equals delta x over Vx. So if I asked you just to stop there and find time in terms of the givens, well, you're done. Now here we can go ahead and plug numbers in. Delta x is 10 centimeters, which is 0.10 meters, and Vx is 4 times 10 to the fifth. And if you divide those out, I get 2.5 times 10 to the negative seventh seconds. Or if you're really cool, it would be 250 nanoseconds. But you would only write that if you are really cool, okay? It's 250 nano. Nano is negative 9, okay? All right, so here's our first answer for the net electric field. Here's our time in terms of the givens, okay? The next thing I asked for is Vy, okay? What's the vertical velocity that the electron's leaving with? He's moving downward when he leaves, okay? So for that process, we're going to use V final in the y direction equals V naught in the y direction plus AT. Okay. Now Vy naught 0 because he's entering horizontally. So you get Vy final. Okay. My pen fell asleep. There we go. All right. Vy final equals A. Well, that's going to be force divided by mass, and then times time. Now I got an expression for time, right? That's delta x over Vx. So we'll come back to that in a second. What's the force? Okay, well, force of a charged particle in an electric field is QE. So we got QE over m, that's your force over mass, and then your time was delta x over Vx. So if I asked you to find Vy in terms of the givens and fundamental constants, that's the answer, okay? Well, I'll take that back. We didn't have E, right? That wasn't a given. Okay, so I got to sub in this for E. Okay, so we got to get rid of that. Oh my gosh. So Vy final equals Q. E is sigma over epsilon naught divided by our m times our delta x over Vx. All right, now everything in there is either a given or a fundamental constant. And I'll tidy this up a little bit. So you got Q sigma delta x over m Vx epsilon naught. Now, the Q and the m, that's the charge and the mass of an electron. Okay, so if I were actually going to plug all these in, okay, let's go ahead and actually get numbers for this. Okay, so this is the expression for the velocity. The actual velocity, the charge of one electron is 1.6 times 10 to the negative 19th coulombs. Sigma, we already know that. It's 100 times 10 to the negative 12th. That's your pico. Delta x is 0.10 meters. The mass of an electron. So that's not one I would expect you to memorize, but it is, if you looked it up, in kilograms. It's 9.11 times 10 to the negative 31st kilograms, very tiny. Vx was the original velocity, which was 4 times 10 to the fifth. So that's 4 times 10 to the fifth. And then epsilon naught is a constant. That's our 8.85 times 10 to the negative 12. Okay. If you do all that in the calculator, and you might want to try this out and make sure you get the same answer I get 4.96 times 10 to the fifth meters per second. Or if you're really cool, you write 49.6 megameters per second, but only if you're cool, okay? All right, so that's our numerical final vertical velocity, okay? So that's check. And then finally, we're asking for the angle. So for that, so we know Vx is this, and we know Vy, we just found it. We're trying to find that angle. So that angle is going to be inverse tangent of Vy over Vx. Now, if you'd like, you can plug all this into here for Vy, and then divide that by Vx. So you would be Q sigma delta x over m Vx squared epsilon naught. Or because we have the numerical values, you can just take 4.96 divided by 4. They're both times 10 to the fifth, so you don't really need that. So this will be inverse tangent of, let's see, inverse tangent of 4.96 over 4. Again, they're both times 10 to the fifth, so that cancels. And when I did that, I got about 51 degrees. Okay, so this angle that it leaves, that the electron leaves at, is about 51 degrees. So this example incorporated a lot of things, right? We figured out the electric field, both the conceptually and then a mathematical number for the electric field that's created by these two plates of charge. Then we figured out how long it would take the electron to get through them. We figured out its acceleration, the electron's acceleration downward, and then what would that make the final vertical velocity, just like in projectile motion. And then we found the final angle it leaves at. So a good news is some of this stuff is like projectile motion, but the tough part is we have a lot of new stuff. We have electric fields. We have force equals QE, kind of like force equals mg, right? And so you're combining new material with material from first semester. So I do hope that example was helpful, and thank you very much.